We now come to the culmination of this section on calculus, the most important and beautiful theorem in calculus relating derivatives and integrals. It's called the Fundamental Theorem of Calculus. So, the theorem says that suppose f is a continuous function on the closed interval a b, then define f of x to be integral from a to x f of t dt for all x between a and b. So, f of a is going to be 0, f of b is going to be the integral from a to b little f of t dt. Then for every x that lies strictly between a and b, the f is differentiable at x and the derivative of f at x is going to be the original function that we started with, little f of x. Okay, the proof is actually not very difficult. We already know the main ingredients in the proof. Let's just try to write down the difference quotient which comes from capital F. So, what do we have? We have f of x plus h minus f of x divided by h. What is this? So, this is by definition is the integral from a to x plus h f of t dt minus the integral from a to x f of t dt, and this whole thing needs to be divided by h. So, I will put a 1 over h up front. Okay, but remember the additivity property of the integrals, that the integral, if I have 3 points a less than b less than c, then the integral from a to c of a function is the integral from a to b plus the integral from b to c. So, using that I can write this first term here as integral from a to x f of t dt plus integral from x to x plus h f of t dt, and of course I must subtract again integral a to x f of t dt. So, these two terms cancel off and I am just left with 1 over h integral from x to x plus h f of t dt. Now, I am going to use something that is given in the hypothesis that the function little f is continuous. So, what does that mean? Since f is continuous, for every epsilon greater than 0, there exists delta greater than 0 such that if absolute value of t minus x is less than delta, then absolute value of f of t minus f of x is less than epsilon. This inequality I am going to actually try to rewrite as two inequalities. What this is really saying is that f of t lies between f of x plus epsilon and f of x minus epsilon. So, I will write this as f of t lies between f of x plus epsilon and f of x minus epsilon. So, now if absolute value of h is less than delta, then certainly between x and x plus h, we will have f of t is less than f of x plus epsilon and is greater than f of x minus epsilon between x and x plus h. We are thinking of h as a positive number, but to compute the limit we also need to think of h as possibly being negative, right. So, it could be that x plus h is less than x. In that case, the integral x to x plus h f of t dt is, by our established convention, the integral x plus h to x f of t dt. This is for h less than 0. Okay, but in any case, if the absolute value of h is less than delta, then between x and x plus h, f of t is going to lie between f of x plus epsilon and f of x minus epsilon. And so, what we have is that the integral of f of t dt between x and x plus h is going to in turn lie between integral from x to x plus h f of t f of x plus epsilon dt and f of x minus epsilon dt. And let us divide throughout by h, because that is the difference quotient that we are looking at. And now we know how to integrate constant functions. This function, as far as t is concerned, f of x minus epsilon is a constant function. So, what is its integral? Well, its integral is just the length of the interval, which is h, that cancels out with this f of h. So, what we get is f of x minus epsilon is less than 1 over h integral x goes to x plus h f of t dt, which is less than f of x plus epsilon. And so, we conclude that the limit as h goes to 0, 1 over h integral from x to x plus h f of t dt is equal to f of x, which is what we wanted to prove. This is the difference quotient of capital F. And so, what we have is f prime of x is the limit as h goes to 0, f of x plus h minus f of x by h is little f of x as claimed.